So let's discuss polynomials as functions. So I'll get back to the general situation. R is a commutative ring with 1. And I have a polynomial here with coefficients in R. So A0, A1, etc. are in R. When I want to think of it as a function, instead of writing it as f, we write it as f of x. And this is basically how you get introduced to polynomials, x cubed plus 5x minus 6. That's a polynomial function. Maybe you can think of it as a function from real numbers to real numbers. You give me a real number, 1, and I can calculate the value of this function. F of 1 happens to be 0. Give me another one, I can calculate the value. 8 plus 10 minus 6, which is 12. That's f of 2. Yeah, so we say 0, because f of 1 is 0, we say 1 is a solution to the equation fx equals 0, or 1 is a root of f. Yeah. So thinking of polynomials as functions is a useful thing to do, we will see. And I want to package this in a definition of something called the evaluation homomorphism. So let's see how that goes. So you have this polynomial with coefficients in R. Take an element of R, little r. Then define, first of all, f of R to be a0 plus a1r plus a2r square plus an r to the n. And here all the addition multiplication is happening in R. So this is an element of R. Okay. So this is called the value of f at R. Yeah. So this way, an f in Rx defines a function from R to R by taking a little r to f of R for little r in capital R. This is called a polynomial function. And still, given this, fix this little r, then you get a homomorphism, at least a function at this point, from the polynomials to the ring R by evaluation at R of f equals f of R. So this is a strange thing, maybe. The input to this function is a function. It's a polynomial function. So you feed in a polynomial into this evaluation at R function, and what it does is it evaluates f at R. So evaluation at 1 of x cubed plus 5x minus 6 is 0. Evaluation at 2 of the same guy is 12, etc. Yeah. And you verify that this is a surjective homomorphism from Rx to R. Ring homomorphism from Rx to R. And this homomorphism will play a rather important role. The kernel of this homomorphism is exactly all the polynomials that vanish at R, meaning that have R as a root. Yeah. So for the rest of this summary, I want to talk about factoring polynomials. And the first are irreducible polynomials. The first result is this rather simple observation, which is nonetheless very, very useful. Let's get back to a field again. let f be a field, a polynomial f with coefficients in the field capital F has a root a in f if and only if x minus a is a factor of f in fx. By the way, I did not write what root means, did I? Maybe I should write here. Say that a in R is a root of f in Rx if f of a is 0. Right? So you have a root if and only if x minus a is a factor. Now let's see why this is true. The point is that if you give me, maybe let's do it here. If you give me an A sketch, I can take this polynomial and divide it by x minus a in any case. I'll get a quotient and a remainder. Now the remainder will have degree less than degree 1 because what I'm dividing by has degree 1. So this guy has degree 0. Or it is 0. In any case, it has degree 0. So it's actually an element of the ring R. It's a constant polynomial. So that's why I'm not writing R of x. I'm just writing R. And then what is this R? If you evaluate at A, so formally apply the evaluation homomorphism at A, then you get f of a on the left-hand side, and you get a minus a q of a plus r. There's nothing to evaluate here because this is just a constant. So that tells you f of a equals r. So what you get out of this is f of x equals x minus a times q of x plus f of a. This holds in any case. So now, if a is a root of f, what does that mean? That means this vanishes. So if a is a root of f, that means this vanishes. F of a is 0, which means f of x is x minus a times the polynomial, which means x minus a divides f. And conversely, that also is clear. Yeah, so the rest it's written in my notes. So that's why this is true. The way this is relevant for factoring is that it tells you when you have a linear factor. Okay, so for example, if you take a polynomial like this, it looks like a polynomial with integer coefficient, but I want to think of this as a polynomial with coefficients in f2. Okay. So this 1 is really 1 mod 2, and this 1 is also really just 1 mod 2. So I want to know whether this factors or not. If it cannot be factored, then we say it's irreducible. Let me make a formal definition first. How about that? Definition. A non-zero, non-unit f in a domain R is called irreducible if you cannot factor it. Meaning if you wrote as a product of two things, whenever f equals u times v with u, v in R, then it follows that u or v has to be a unit. Of course, you give me a polynomial, I can write it as a unit times another polynomial. Yeah, I can pull out a unit in any case. That's not really factoring. If I'm working in QX, for example. Yeah, but this is not considered factoring. Factoring means that you have to actually have some non-units. So that's a proper factorization. And things that cannot be properly factored are called irreducible. So I'm claiming that maybe this is an exercise. Show this thing is irreducible. And the reason is that if it has degree 3, so if it factors, if fx factors, then it would have a degree 1 factor, because only where degree 3 can factor is a degree 1 times a degree 2. Would have a degree 1 factor. Hence, a root in F2 by this lemma down here. But it doesn't. But you can see if it has root or not. F2 has, after all, just two things, 0 and 1. If you calculate F0, it's 0 plus 1, which is 1. If you calculate f of 1, it's also 1 plus 1 plus 1, which is 1 in F2. So f doesn't have a root, so it doesn't have a degree 1 factor, so it doesn't have a factorization at all. The other thing that I want to quickly touch upon, there is more detail in the notes, is this reducing coefficients. What that means is that if you have this f in Rx, and if you have an ideal in R, two-sided ideal, we are talking about commutative ring anyway, then there exists a homomorphism from, let's call it alpha, from Rx to R mod I x, obtained by reducing coefficients mod I. What I mean is, let's say you take this polynomial x cubed plus 3x minus 7 and think of this as a polynomial in zx. Okay, I can apply this alpha mod 2, so I'll take the ideal 2z, and I can apply this alpha and I'll get a polynomial. Now I just want to do, what I want to do is I want to think of these coefficients as elements of f2, z mod 2. So this will be x cubed plus x plus 1, because 3 minus 7, they're all mod 2 in z mod 2 x or f2x. And you check that this is a ring homomorphism doing this. And this is useful because if the original guy factored, then this would also factor. But we know that this is irreducible, we just saw. So it follows, there's some detail to check here, but it follows that G is also irreducible. So this is a useful tool to check irreducibility.